Modern technology. Okay, great. So yeah, this talk is about something completely different, namely not about types. It's about the fundamental problem of reasoning about equivalence of programs, in particular in the context of languages with a notion of state and variable store. And because it's more fun to do this using category theory, we want to use category theory to do that, to achieve a more fundamental and basic and principled way of reasoning about this. So let me try if I get it to full screen. Okay, doesn't seem to work. So let me start with a very simple toy example. So we take our textbook Y language that you see in every introductory course on programming languages, and I ask, are these two programs equivalent? Do they do the same thing? So the first one puts x to 10 and then decrements x until it reaches 0, and the second one puts x to minus 10 and then increments x until it's 0. So are these programs equivalent? Well, that's a nonsensical question because I didn't tell you what equivalent means. And in fact, there are various ways to answer this. So if you take your standard big step or natural semantics, that we also like to call termination semantics, then they are equivalent because they generate the same final state, namely at the end in both programs x is 0, right? But you can also, for example, look at cost semantics, which means you not only take the final state, but you also take into consideration the number of steps to reach it. And in this case, both programs take 10 steps, so they are also cost equivalent. But another sensible notion of semantics is trace semantics, which means you consider the sequence of states generated by the program. And in this case, obviously, the sequence of states is not the same, although the final state is the same, right? So they are not equivalent under trace semantics, right? So this is these are notions of semantics that we would like to reason about. And a nice property of each of these three kinds of semantics is that they yield a compositionality property, namely, if you take two equivalent programs and put them into any context, for example, into the context of a while loop, then these two more complex programs remain equivalent. So this is called compositionality, and it means that you can reason about equivalence of programs by just looking into simpler subprograms, which is obviously something that you want to have and that every good notion of equivalence should satisfy. And yeah, this is the kind of theorem that we would like to reason about at an abstract level. And why do we want to do this? Well, the proof of this kind of statement is obviously, if you state it like this, specific to the language and also specific to the notion of equivalence. So even for the simple Y language, you would really have to give 3 different proofs of this theorem, which, okay, is doable for the Y language, but if you talk about languages that are more complex, that have features like higher order store, for example, or functional features, this can become really complex very fast. And so we would like to go for a more uniform approach. And the approach that we take is a Bialgebraic approach that is based on Turi and Plotkin's abstract GSOS, which I will recall in a minute, and on its higher order extension that we recently developed in a series of papers starting at Popple 23. So, so what is abstract GSOS? This was developed by Turi and Plotkin in the late 1990s, so it's a quite classical approach to reasoning about equivalence of programs using category theory. And what they did is they started with the observation, so what are the ingredients of a programming language, like the Y language? So typically, you have a syntax, so you have a specification, some grammar that specifies which terms you have. You have operational rules that explain how the programs evolve. So in this case, rules that explain how programs transform the state. The state, in this case, just being an assignment of variables to integers, so very simple. And these rules induce an operational model, which is a kind of transition system on the set of programs. So in this case, you take a program, you take a state, and then you either move to another program and another state, or just to a state terminate, right? And the key observation by Turi and Plotkin was that you can abstract all these ingredients in a very nice and natural way. Namely, The syntax, as we just heard in the first talk, can be modeled as an initial algebra for a suitable signature functor. So in this case, it would just be a functor on set, but for example, if you talk about a lambda calculus, it would be a functor on some presheaf category or nominal sets of some kind. The operational model can be then abstracted to a coalgebra for a suitable behavior functor B. So it's just a coalgebra on the set, on this object, mu sigma of program terms. And crucially, the operational rules can be modeled using this notion of a GSOS law, which is a natural transformation of this kind. And the idea is that this is a function that encodes the rules into a family of maps. So what this map says is, you give me some operation from my language, like sequential composition. You tell me for each of the operands what its one-step behavior is. So in this case, for example, I tell you from P and S I can go to P prime and S prime. And then I tell you where to transition into next. So the sigma star here is the free monad, so you can transition into arbitrary terms. Yeah? So a GSOS law is just an encoding of a set of rules into a family of natural functions. And yeah, this is really the key idea by Turi and Plotkin. And what they showed is that at this level of abstraction, you can actually reason about program equivalence. They have a compositionality result that says, in any of these settings, strong bisimilarity on this coalgebra of program terms is always a congruence, with a categorical notion of congruence that I will not state here, but there is a categorical abstraction of saying what a congruence is. So this looks very useful. It's a compositionality result for free, but unfortunately, in the context of stateful languages, it is completely useless. And this is because it talks about strong bisimilarity, and strong bisimilarity on this set of while programs corresponds to what is called a resumption semantics. And this means that you have an observer that can, at any point of execution, read the state and also modify the state. So, for example, if you take these two programs, the first one sets x to 1 and then to 2, and the second one sets x to 1 and then increments it. I think every reasonable person would say these should be equivalent, but they are not under resumption semantics, because if you take an observer that after the first step sets the state to something else than 1, say 3, yeah? Then after the second step, the first program is still 2, but the second one would be 3 or 4, right? So by interfering with the state after the first step, you can distinguish these two programs after the second step. So they are not equivalent under strong bisimilarity. In fact, it is difficult to find any non-trivial examples of equivalent programs under strong bisimilarity. And so while we get a compositionality result for this, it's not really useful because it's far too fine-grained semantics. So we want trace, cost, and termination semantics, right? And yeah, people have thought about this problem. There is a series of papers by Abu Saleh and Pattinson from about 15 years ago, where they develop abstract GSOS theory over Gleisli categories for state monads. It's quite a complex theory. And what they can do in the end is cost semantics in this setting, but not trace and termination semantics. And what we propose here is something that we think is an improvement of this. Namely, it is developing abstract GSOS over two sorted sets, so a much simpler setting. And it covers all three kinds of semantics. And in the rest of the talk, I'm going to explain briefly how this works. And yeah, the key idea is to divide programs into two kinds of programs, namely readers and writers. So a reader is like an ordinary program, so it expects a state to be given and then just runs it. And a writer is a running computation, so it's a program that already has a state and eventually might produce new states. And before going into the syntactic details of how this is implemented, let me see what we want to achieve with this. So the operational model of the while language, as you recall, looks like this. It's a transition system on programs. And in this reader-writer extension, we get a two-sorted core algebra. So we have a set of readers and a set of writers. And the behavior is like this. So a reader expects a state and produces a writer, because the writer already has a state then. And a writer can either produce a new writer and a state, or it can silently transition into a new writer, or it can terminate in a state. 3 different kinds of behaviors. And the nice thing about this two-sorted structure is that now one can see that trace, cost, and termination equivalence correspond to forms of coalgebraic weak bisimilarity. So for every coalgebra of any type, you have an abstract notion of weak bisimilarity. This is something that the theory of coalgebras gives you. I will not go into technical details here, but these notions exist, and they are parametric in what is called a relation lifting. And by choosing different relation liftings, you can basically make a choice that you can ignore silent transitions, or that you want to ignore intermediate states or combinations of these. And then you can model, in particular, these 3 notions of program equivalence in this two-sorted setting. Yeah, so this is good because it means that we get a handle on these different notions of semantics using a coalgebraic concept. Yeah, and now I just have to explain how, in the case of the while language, this is implemented. And here's how it's done. So a reader is just an ordinary while program. So the syntax is exactly the same as before. And a writer is one of 4 kinds of programs. So we have this term called bracket PS, which is parameterized in a state. So the state is part of the syntax here, and intuitively should behave like P given the input state S. Yeah? Then we have a term called S.C, which says output S, then behave like C. Then we have a term read S that should output S and then terminate. And then we have another kind of sequential composition that says run C until termination, and then run the reader queue on the initial state of C. Yeah? So it's quite a simple kind of extension. And so what does this do semantically? Let me explain it in an example run. So here you have a run of your standard while language. So it's this loop that we have already seen. And what you would do is typically you would unfold, you take the first x to x minus 1 out, and then output the state 10, and then do this decrement, and so on. Yeah? So this is how you typically run while programs. And in this extension, you do it in a more controlled way, but in the end, you output the same sequence of states. So we start with this program, and in the first step, we will basically pull out the x equals x minus 1 and tag the program with the current state. Then we output the current state. This is what this dot operation does, output the current state. Then we pull the tag into the x equals x minus 1. This is a silent transition, nothing happens here, no output. Then we actually execute the decrement. So now the program is turned into a read x minus x1. So and read x9 means output the state x equals 9, and then continue in this way. Yeah, so this is basically equivalent to the previous program. We output the same sequence of states, but we do it in a more controlled way, where at every step we tag the subprogram that we currently evaluate by the current state, and then do the output. Yeah, so it's just a more convoluted way of writing the ordinary evaluation of a while program. But, as I said before, now we do this in this two-sorted setting, and therefore we can talk about trace, cost, and termination semantics in this setting. And so we can hope that at this level of generality, we should be able to get a congruence result for equivalence of programs. And in fact, we have this. So I mentioned this result by Turi and Plotkin, this nice but pretty useless result about strong bisimilarity. And there is a generic result about weak bisimilarity as well in the setting of abstract GSOS that says if you have a sufficiently nice language modeled in abstract GSOS, then weak bisimilarity on its operational model is a congruence, where weak bisimilarity here, as I said, is parametric in a choice of a relation lifting. So you get different notions of weak bisimilarity by different choices of liftings. And being nice means that the rules of the language are polymorphic and they respect weak transitions in a suitable way. And you can make this formal using diagrams, what this means. So we have this result, and now we can just apply it. And we get the compositionality theorem for a while that I showed at the beginning of the talk as a simple corollary of this generic result about weak bisimilarity for stateful languages. So, of course, what is not so interesting is the fact that we get this result, that we get this corollary, but that it's generic. So we get it by just choosing categorical ingredients and get this result almost for free. And what I should mention here at the end is that this is, of course, a principle. Yeah? So I showed how this works in this very simple-minded while language. But in principle, you can apply this to every kind of stateful language. Yeah? You just take any stateful language, you do this reader-writer decoupling with these artificial operations that tag programs with the current state. And in particular, you can, for example, apply it to higher order languages. And this is also something that we did in the paper, and I don't have to have the time to go into details here, but in this recent work, we developed this theory of higher order abstract GSOS, which is GSOS for higher order languages, based on the very simple idea of replacing this behavior endofunctor by a suitable behavior bifunctor that is contravariant in the first component and covariant in the second component. And maybe I can give you the gist why it's a bifunctor. Let's go back to the first slide. So here is the functor for the Y language, and you have this to the S in the exponent, the W to the S. Here the S is just a constant, so it's just an endofunctor. But in a higher order language with higher order state, the S itself would be dependent on the set of programs, because a higher order state means you can store programs in the variable store, right? And so in the higher order setting, this becomes a bifunctor where the contravariance is because of the component of the exponent. And one can run this abstract GSOS theory in this higher order setting. And what one gets is an abstract theory of bisimulation that is sound for contextual equivalence, and we have worked out several examples of this in the paper, so you're invited to read about this. Okay, thank you.
Questions?
Yep.
Hello, Max New, University of Michigan. So the two I'm trying to wrap my head around the reader-writer distinction. So I remember you had a paper at Popple that was called by push value GSOS, abstract GSOS stuff.
Yep.
This is not related to the call by push value. It doesn't seem to line up to me, but
no, not right now. So if you, this is just a simple first order language at this point, right?
Yeah.
In principle, you can apply this whole framework.
Sorry, I'm asking, is this distinction related to the value computation distinction in call by push value?
Well, it's a good question. So it's a bit analogous. It's not call by push value, but it's analogous in the sense that you have an explicit translation of readers into writers using this tag notation, right? So in a way, it is in spirit similar, but it's not call by push value.
Right, like the readers include stateful updates, so they're very much not pure values.
Exactly, so it's not the same thing, but it's inspired by the call by push value paradigm. Yeah.
Thank you.
Yeah.
I have a question. So the reader-writer distinction, so that's a more fine-grained language than like the Y language that you showed. So are there multiple ways to add this extra information to the Y language or is there a standard way to do this?
Well, there are obviously some design choices that you can take. It took us quite a long time to get it right. to get it right in the sense that the semantics of the extended language is the same in the sense that the output sequence doesn't change of the states. Yeah, and yeah, I would say that there are some design choices, but for example, this principle that you want to tag the states with so this bracket operation, I think this always must be there. And in the other operations, there might be some choices how you control it precisely. But the first one, I think, is really the fundamental one. This is necessary, absolutely. Yeah.
Okay, one more question. Last question.
Oh, I'll do it. Here, question.
Okay, then you go. Sorry.
Macquarie University, Jinyang Zhang. I think do you have any plan to extend this system to other effect systems, such as exceptions or any other that kind of effects?
Sorry, what was the last word?
Sorry?
I didn't get the last part of the sentence. Such as what?
Exceptions or such as
sure. So, I mean, obviously, one key goal would be to apply this to effectful languages in general, right? Where you have possibly even a monad as a parameter. We're not there yet, but I think exceptions would be a very natural next step to if you want to go for a specific effect. But we haven't done this so far.
Okay, thank you. Let's thank the speaker again.
Okay, thank you.